here we go. This is lecture 8 in high dimensional probability, and we're going full speed at concentration inequalities. Concentration inequalities for sums of independent random variables. And the last time we proved state of the art, very powerful, basically optimal inequality for sums of Bernoulli random variables. That's probably all you will ever need for if in your future career you have a problem about counting different events and you want to see concentration. Chernoff's inequality is the most powerful one. Chernoff inequality applies to sums of 0, 1 random variables. So we're called them Bernoulli pi. So this is Bernoulli. And the notation simply means that xi takes value 1 with probability pi, yeah, and value 0 with the remaining probability 1 minus pi. So we look at independent Bernoulli random variables. We sum them up, n of them, like this. Sum of 0 and 1s will get us some number, and the mean or expectation of the sum. The expectation of each xi is pi, and so the expectation of the sum is the sum of pi's. Let's call this value mu. And we proved this tail. Basically the inequality says the sum, if this is kind of the probability density function, although it's discrete, the mean is here, and this is a probability that Sn is greater than t, and we would like it to be small. So we want to say that the tail is small, and this is how small. And this is a funny expression. I don't really remember it because it's not Gaussian. We call it a Poisson tail. It's very sharp. So that's what we proved. Most of the time, if you will ever apply this inequality, you will apply it for the same pi's. If all pi's are the same, then Sn is the sum of Bernoulli with the same p, and that's called binomial distribution, right? So if all pi's are the same, then they all equal mu over n, just from this. Is all terms of the sum are the same, then all of them are mu over n, and then Chernoff's inequality works for Sn, which is distributed as binomial distribution, binomial, n trials, and probability of success is mu over n. So one thing you need to remember, if you ever have a binomial distribution, if you're ever counting some events, then Chernoff's inequality is the best. Basically, it gives you all the best concentration for that. Okay, that's where we stopped last time. Good, that'll be our tool that we will use and try to see what it tells. Any questions before we go? We're good? Okay, a couple of remarks about Chernoff's inequality. You know what, this tale is funny. It's hard to remember, it's hard to understand what it really means, but really this Poisson tale is what? The main thing is that there's t here and t here. So it's if you forget all these e and m's, it's scales like t to the minus t, which is e to the minus t log t, which is heavier than the Gaussian tale. Which is e to the minus t squared over 2, because t log t grows slower than t squared over 2 a little bit, and then so we get a little bit of, we don't get the Gaussian tail in the full range, but that's okay. This one thing that is very useful, the Chernoff's inequality is useful for, is when t is very large, and this is where we have Poisson tail. T grows to infinity, you have Poisson tail, great, it works. And also, surprisingly, it is useful where t is really close to the mean. Usually you think like t's should be very far from the mean and get the small tail. No, actually in this case, the Chernoff's inequality is really strong, even if t is very close to the mean, and that's what we'll note now. So we'll call it small deviations, the small deviation regime. Small deviations if t is very close to the mean. Let's say just give it a little kick to the right. Let's say 1 plus delta times mu, and think of delta with delta very small. So we'll kick it to the right a little bit and see whether Chernoff's inequality can still give us a good answer. By the way, let me ask you this question. If t was exactly mu, what do you think should the answer be? Probability that the sum is greater than its mean. What's your first reaction to this?
1/2.
1/2, yeah. If it was a median, it would be exactly 1/2, right? The median is defined this way. The mean and the median they're cousins. They should be too far from each other. So probably something like a constant, maybe 1/2, maybe a constant. In fact, it will be e. I think 1 over e, if you check this correctly. But the point is, that we shouldn't get anything for any random variable. We shouldn't get any small number this way, right? The probability that Sn is exactly larger than the mean, it should be something like a constant. So it is surprising that if you step a little bit to the right, just tiny bit, we'll get a very good result then. Let's do that. So delta is small, we let t be this, and let's just do this asymptotic analysis on the Poisson tail. Okay, let's make this asymptotic analysis about delta. So, okay, so I substitute this t here, e mu over t. So mu cancels, and I get 1 plus delta here. And t is 1 plus delta mu. Okay, so far so good. So I will collect, okay, happens here, e to the minus mu will cancel with e to the, e to the minus mu, and there is e to the mu, I think. So that will cancel. Okay, so I think what's left is e to the delta mu here. Yeah, and just that thing, 1 plus delta times mu. I just canceled e to the. All right, let's make this a single exponent of something. So what is this? Mu will be the common factor. And there's delta minus 1 plus delta log 1 plus delta. I don't know what it is. It's some weird weird expression. Okay, so far so good. Yeah. Okay, it's weird. Nobody likes this, right? How do we know what this is? But remember, we're looking at delta small. So I computed this Taylor expansion about 0. And when delta is small, it gives me about delta square over, don't write this down yet, I'll change this in a second. Delta square over 2. If delta goes to 0, that's from Taylor expansion. If you do your calculation, do the MATLAB. Actually, minus delta square over 2, that's important. Okay, and then a miracle happens here. We get E exponential of what? Of minus delta square over 2 mu, and that's Gaussian tail. Remember, delta square over 2 is a Gaussian tail. So we get a Gaussian tail around the mean. That's great. It still works. But we shoot for a non-asymptotic result. I can't really take limit as delta goes to 0. So let's give ourselves a little bit of room. I did my calculation offline, did my homework kind of, and I found that this is at any rate, this is less than minus delta square over 6. 6 is an arbitrary number, but I just want to make sure that this happens always for all delta, not just in the limit. And this is by Taylor's expansion. Do it yourself. Okay, good. Yeah. So we have a pretty good result. The sin is greater than if you just step a little bit to the right of the mean. We get e to the minus delta square over maybe 6. Good. Agreed? Okay. The way I remember this result is that if you step a little bit to the mean, should be mu. You guys missed it, and I missed too. Should be delta squared mu over 6. And that's important because it is mu, the mean, that drives this expression large, right? We want something large here. Large negative number. That's why the probability will be like small number. So the probability is exponential in the mean. So if you count some events, how sure are you? What is your confidence level about the probability? It's exponential. You're exponentially confident in the average number of these events. The more events you have, the more you're sure. That's a great result. Right? You become exponentially. The more observations the more observations we accumulate, the more sure we are about the result in statistics. That's not surprising. But it is surprising that we're become exponentially sure about the result. That's why it is important. Okay, so that's small deviations. Good. Any questions? Good. Okay. Chernoff's inequality only gives you a one-sided tail. Only this tail right there. And obviously, you would like to have double tail, and it's similar. So the lower tail is similar, and this will be a problem in homework 3. Prove the other tail in Chernoff's inequality. And so, in fact, you can then combine them in one result. And I'll just state Chernoff's inequality for small deviations for this one. So this inequality says if I step delta mu to the right, the probability will be small. And the same result holds if I stay delta mu to the left, the probability is small. So if I step in any directions from delta mu, the probability will be small and we'll just pay a factor of 2. Okay, when you do it by yourself, if you have homework example, if you have homework problem with the other tail, then you combine them by union bound. Just take the union of these two, intersection of these two events. And, okay.
So the distribution here is not actually symmetrical, but we still have the bound as if it was symmetrical.
Mm-hmm, exactly.
Just multiply by 2.
Mm-hmm. Yeah. We have. The distribution is not symmetrical. It's discrete, but I'll pretend it's not. It's continuous because I can't really. Wait. Okay. So this is non-symmetric distribution, and this is mu here. But yes, it's surprising that we have the same bound on the right and on the left. Same kind of bound on the right and the left. Maybe it becomes a little bit less surprising if we note that around here, around mu, there's curvature, and the curvature is kind of symmetric, right? It doesn't yet see the tail. If you zoom in, you don't really see how non-symmetric it is. So around here, this is how I explain this phenomenon. Around here, maybe if this is like delta here, we have something like a Gaussian behavior, Gaussian regime. So if you zoom in, if you're like a little spider, if you zoom in, you see kind of a bell-shaped curve forming. You don't see the tails just yet. But if we step out of this long enough, then we see a heavier Poisson regime. It's like e to the minus t squared over 2, and this is t to the minus t. E to the minus t log t. So it's kind of symmetric in the beginning, and that's why it shows in this proposition, and then it becomes non-symmetric. Good. Okay, cool. So we built ourselves a very powerful tool with which we'll then study different applications. The first of which will be for networks, for the analysis of networks. Okay. In data science, there are different objects that we see often, populations, and one of the most important objects that we see over and over is a complex network. Networks. Networks is basically a graph. And the graph consists, if you want to specify a graph, you specify the set of vertices and the set of edges or connections between them. So for example, this will be a graph. I will connect some of the vertices, maybe not all of them, just like this. There are these vertices, 5 vertices, and there are some connections between them. The real world networks can be very complicated and very complex. For example, biological networks. Let me show you. One of the most important biological networks is, of course, the brain, and the neural connections in the brain, where you have neurons as vertices and their tentacles. Neuron, and each neuron has little tentacles. I think they are called axons, and this is a neuron, and they are connected by these axons, and they send information. They talk between each other. This way, it's a very complicated system. There are social networks such as World Web, Internet, network where vertices are pages, web pages, and the connections formed by links between them. This graph is actually directed because the link actually links from a web page to the web page, but for now, let's ignore that. And this is a visualization of that very complex graph. There are other biological networks that are very important. For example, protein-protein interaction networks. This example is for yeast, where we have protein and proteins, and they also talk to each other in some way. They affect each other. Or more generally, signaling networks in biology, where different biochemical substances, proteins in particular, but not only, hormones, for example, they send signals. Like start digestion, go to sleep, wake up, lose your hair, whatever. So these hormones talk to each other, and they form a very complicated system, which is important to understand, even in one cell, because that's how we understand how cell works. So yeah. What else? Anybody has any other example of a very complicated network? Transportation network, maybe? Electrical network? Give me one more example. Hey, you're sleepy today. What's going on? Give me an example of a network that I haven't mentioned.
Like some telecom network.
Yeah, telecom network, for example. And this is where what? This antennas talk to each other, or what are the nodes? What's their?
It's like phones talk to antennas, and antennas to other antennas, and so on. I suppose.
Yeah.
Or maybe also, but it would be one way, like talking to satellites, like this internet, like something like Starlink or something like this.
Yeah. Well, there's Starlink is a good example. Yeah, it's a dynamic network in sense, because the antennas talk to the satellites. Oh no, it's not dynamic, it's static, because satellites, I think they're on a fixed orbit, right? They're exactly above that. Yeah.
No, I think they move.
Like,
okay, so
they're not geostationary for Starlink.
Okay. So yeah, so it's dynamic network then. They pass and then they talk to the different ones. Yeah, that's a great example. It's a little more complicated because the vertices play different roles. There are vertices that are antennas. There are vertices that are satellites.
But I didn't hear if you say like network of friends in some social network.
Yeah, exactly. Social network is a great example. On Twitter, Facebook, whatever. On your phone, your contacts. So huge. Just physical social network, right? Those people, there are what, 7 billion, 8 billion people in the world, and we just can connect the people who say they're friends with each other. So that's a huge network.
Maybe all things that can send information are networks. It can be internet, it can be telephone, it can be something another, maybe.
Yes, any network that occurs in where the information flows, kind of like the information is passed through. So engineering, yeah. Perfect. Those are family trees, right? Exactly, family trees, right? Father and so on and so forth. And they're trees, but they're not exactly family tree, right? So your ancestors and your children and so on and so forth. For you, it's a tree, but then as people marry each other, the trees join each other, and so it's the result is not exactly the tree, but it's some very interesting graph. Yeah, that's another example.
Acquaintances graph.
What graph?
Acquaintances, when you join the acquaintances.
Yeah, like friendship, acquaintances. Yeah, there's a lot of these graphs where you actually want to understand the structure of. You want to catch bad guys on a social network, for example, or you want to see if there are certain communities that form and how they form and so on. You want to understand the brain, how it works. And so the first thing a data scientist might want to do is to build a model, a simpler mathematical model for a complex network. How can we form as mathematicians, as probabilists, a model for brain network, for social network, let's say? Well, nobody knows really. But one of the simplest models is this. Just take all these people, let's say 8 billion people, and then form connections at random with certain probabilities. Right? Let's say I can form a connection from here to maybe to India with some small probability for each person, maybe 0.0001. And I form connections with my neighbors in the city with larger probabilities, maybe probability 0.3. But make them random, right? So probabilities are fixed, but connections are random. They're formed randomly. I may befriend somewhere or may not. And this way, we'll get a huge network, which we call a random graph. Understood? Yeah, so this is our model for a complex network. We impose independence, which is not exactly the most natural thing to do. In real world, it doesn't work, but we form friendships independently with people, but with different probabilities. Very surprisingly, this becomes already a too complicated object for mathematics to study. And so we need to make one more simplification and study the next simplification of this model, which is where the connections are formed with the same probability. Okay, this is totally way out, like doesn't really happen in the real world. But we really need to understand this basic thing before we move to the next step. So the most basic model, kind of the ground zero model, the ground zero model for a network is a random graph. In this particular model was proposed by Paul Erdős and Erdos-Rényi in, I think, 1952. G and P, Erdős-Rényi random graph. Erdős-Rényi model. Random graph. G and P. Okay, here where it is, so we fix a set of N, let's say capital N vertices. Think of all the people on the Earth, and then we connect each pair of vertices with an edge independently and with probability P, with fixed probability P. An oversimplified model of any network, but we have to start somewhere. So this is okay, good. Okay, guys, hold on. Let me show you what it looks like. So this is a simulation for what happens if you take 200 vertices and P equals 1/40. So you have some graph. This way you get some random graph. This way. the larger P, the more dense, the denser the graph is, obviously, right? Because there is more probability of forming a connection. The smaller P, the sparser the graph is. And here's what happens if P is 3 times smaller, I think, or twice smaller. P equals 100. Some vertices are isolated, and like these are isolated, and some vertices form hubs. And there are very interesting trees growing out of this, and there are no cycles. And you can ask all these questions then, right? There's always, you can say, wow, this is so beautiful. So will there be isolated vertices with high probability at some P? What is that P? Will there be hubs forming? For small P, do we always have only trees? Is it always a tree? Or maybe there is a cycle? Maybe there is a triangle somewhere. Is it a coincidence that we have a tree here or not? What are these objects? This is so interesting. Then you can, it's like a funnel. You get on the hook with this problem, and you can study your entire career, the GNP, this model, Erdős-Rényi graph, and ask these different questions about it. Is this graph always going to be disconnected for some P like this? So there are different components. Oh, yeah, okay, a lot of questions. Okay. One important thing that people have found, Erdős and Rényi, in the very beginning, is that this model of random graphs behaves almost like a physical object, almost like physical substance, in the following sense, that it undergoes phase transitions. Like physical matter undergoes transition from a solid state to a liquid state and then to a gas. Also, Erdős-Rényi model undergoes similar phase transitions as you drive P, let's say from 0 to 1. If P is 0, there is no chance of connection, and all vertices are isolated. Right? Then some vertices start to form connections, and then they start to form trees, and then suddenly cycles start to appear, and there are still disconnected components that don't talk to each other. And then at some point, if P grows, the components all merge to each other and form a giant component on the outskirts of which there are still little points, and then those little points join in and form big cycles, and this is amazing. So, and then at some point, everything becomes totally connected. But this is not the most surprising thing. What I describe is, of course, it should be that way, right? What is the most surprising thing is the sharpness of these phase transitions. Is that it's not just growing. It's like this: you slide P from 0 to 1, and nothing happens, and these are still isolated. You can just make your own experiment in the computer. You slide P from 0 to 1, nothing happens. All these vertices are still isolated, and they're little talk to each other. And then suddenly, at a very specific P, suddenly something happens. It's like a phase transition, right? There is nothing between gas and liquid, or between liquid and a solid state. And so here, exactly here, the same thing happens. Suddenly, the graph is disconnected with very, very high probability, and you slide P just a little bit up, and the graph is connected with very high probability. So it goes from probability almost 0 to probability almost 1, almost instantly. And whenever you ask about some transition, for example, from disconnected graph to connected graph, from no cycles to cycles, from no isolated vertices to, from isolated vertices to no, and so on and so forth. Whenever you ask about something, there is always the same phenomenon. There is always this sharp transition that happens at some P, almost like as if this was a matter, physical matter. Amazing. So, okay, this is, yeah, I should not probably talk too much about it. This is absolutely amazing object. And what I just mentioned here is that there are phase transitions, almost like in physics, phase transitions occur. Let's actually give you a couple examples of these phase transitions. But before that, let's call the degree the degree of a vertex I, called, let's say, DEG, degree of I, is how many friends it has, or the number of edges connected to I. So, for example, the degree of this vertex I is 4. There are 4 other vertices connected to it. What is the distribution of the degree if I fix I? For each vertex, just think, right? We have a vertex, fix a vertex. How many friends will it have? Well, let's think how the model is formed. Each person, other vertex can be a friend or not, independently, right? The friendships form independently. There are capital N people total, and with each of them, that vertex can be friends or not, independently. So what is this distribution then? How many friends does it have? The distribution is not Gaussian, it's not Bernoulli, it's Poisson. What do you know?
Bernoulli.
Bernoulli almost. So Bernoulli is 0 and 1.
Uniform?
No, uniform is like any value is possible with the same probability. Right? And that's probably not true, right? We shouldn't, if I just make friendships independently with very little probability, then probably it's not true that I will have any number of friends with equal probability. No, some friends are more likely, some friends. Not uniform. Bernoulli is 0, 1. Either I have no friends or I have 1 friend. Like, not exactly, right? But what?
Poisson?
Binomial.
No. Okay, so we make an experiment, right? We're making trials, independent trials. Each friend is a trial. Sorry, each person is a trial. Yeah, exactly. Each person is a trial, whether a friend or not. And we look at the number of successes here. So binomial, right? Somebody said that. It's a binomial distribution because we have n, actually not n, we have n minus 1 people, because I can be friend with I'm friend with myself, but that's not what we do here. There are n minus 1 possible friends, and each one actually is a friend with probability p. So the number of successes, number of friends, is binomial. In particular, the expected degree of a vertex is n minus 1 times p. N minus 1 friend, and 1 is 1 possibilities. Each realizes probability p. So n minus 1 times p. Let's call this d, this number d, the expected degree. It's how many friends you expect to have in this model. Every vertex expects the same number of friends. So I brought this up because phase transitions are easiest to describe in terms of d. If d is about 1, okay, so if d is less than 1, let's say, if the expected number of friends is less than 1, it's an extremely sparse graph. There's a lot of isolated vertices, and most of them are isolated. And all you see is probably a picture like this. What is it? Yeah, it's probably a picture like this. Even less so, but something like that. Lots of isolated things are floating here. But if d slides above 1, and when I say slides, it's really, really sharp. It's like slides from 0.99 to 1.01, for example. As soon as you make that slide, a giant component appears. Giant component appears. And in this picture, the giant component is already kind of forming here. the giant component is a connected component that has much more vertices than all others. Okay, in fact, everything else, the total size of everything else will be logarithmic compared to that giant component. So it's exponentially larger giant component occurs. Suddenly things start to form together. If D, and then you slide further. You slide. And if D is about log n, and by log I mean again, it's a natural log. So it's from like 0.99 log n to 1.1 log n. Exactly at that moment, the graph becomes connected. So connectivity occurs. So here's the graph is disconnected. There are different components that float. But as soon as we slide D above log n, the graph becomes totally connected. There is no disconnected vertices. Everything is connected, the same component. Okay. And there are like 15 different transitions that are as beautiful as this, and you can see Wikipedia for others. What we will do today is we will establish a phase transition, one example of this phase transition for regularity. The phase transition for regularity. I'll explain what this means in a second. So a graph, let's call it D regular. If everybody has the same number of friends, if degree of I is D for any I. Everyone in this graph has exactly the same number of degrees. That's regular. Okay. Okay, people, give me an example. Okay. Let's everybody think about two regular graph. Well, okay, two regular, yeah, two regular. Okay, think of an example of a two regular graph. How can this be that everybody has exactly two friends? Not
the
one.
points on the circle.
Yeah, exactly, like this. Yeah, thank you. That's two regular random graph. It's called a cycle. Any other examples of a two regular?
Two
Couple
cycles.
of cycles.
Two cycles, yes, two cycles. And I think that's it. I'm not sure, but I think that's it. There can't be any other, no, three cycles, obviously, but any two regular graph breaks down into cycles. I think that's it. You can't have anything else. Perfect. Three regular graph. That's harder, actually. Surprisingly. But here's an well, three, okay, sorry. Triangle, no, triangle is not good. Four. I think this is a three regular. That's a regular graph. And this is a three regular graph too. I just do this and this and this. Good. And so on. We can keep playing with this. Four regular, five regular. So what we will show today, and maybe Wednesday too, is that at d log n, at the expected degree log n, there is a phase transition. So this is a phase transition for regularity of the random graph of G and P. So if D is, let's say, greater than log n, it's a sharp transition, but we'll make a weaker statement. If D is greater than log n, then the graph is almost deregular. So this network is dull, is not interesting, because everybody has the same number of friends, no communities form, nothing. Everybody is like total, I don't know, zombies. Everybody's the same in this network. This is not very interesting network. And if D is less than log n, then the graph is actually very far from it, very far from regular. We will in particular show that there will be hubs, high degree vertices. Hubs, like, I don't know, social influencers, travel bloggers, very high, very popular people. Okay, good. In some sense, it says that this is a regime that's most interesting. Because if you want to model something real with this, you better have high degree vertices and isolated vertices, and there should be some variety in nature. And so that is how we should do that. But let's prove this. So there are two statements here. One will formalize the first statement, the regular, in this way. So if D is greater, and we'll prove a kind of a weaker statement here, but that's okay. C log n, where C is an absolute constant, maybe 10. Then G log capital N should be capital N all the time. Then G and P is almost deregular with high probability.
Can I ask a question?
Yeah.
Could you please clarify how G and P depends on D? Like it looks like G and P is like separate object.
Yeah, yes. So N, P, and D are connected with this equation. So when we say that D is greater than log n, for example, I could have written this as D. So P over D is what? D is NP. So P is greater than log n over n minus 1, but I can skip n minus 1.
Yeah, okay, I get it. Thanks.
So this is a transition. Yeah. Good, everybody understand that? Yeah. So G and P here, maybe let's make it here. Clarification, D equals n minus 1 times P. That's, yeah, so it's if the graph is a little bit denser than log n, then it's deregular. So everything is the same with high probability. And the meaning of this that with probability at least 0.9, let's say, doesn't really matter, 0.9, every vertex has about the same degree. Very close to its expectation. And these numbers that I put here, the 0, 9, 1.1, there, I could, from the proof, you will see that we can put any other number even closer to 1. I just don't want to put too many parameters. Here. Okay, good. Understood? Statement clear? Perfect, let's do it. Okay, so the statement is kind of hard because it wants something happen for all the degrees of this, all degrees at the same time, all vertices. So let's make it simpler first. Let's fix I, fix a vertex, and look at that specific vertex. Fix I, and then look at what this event, let's call this event somehow, maybe call it EI. This is my event, the good event, that it's very regular. Well, we know that the degree is a binomial random variable with average what is it? Now let me scroll up. Binomial, it's binomial with n-1 and p. So it is, let me just write that this is a binomial with mean, with expectation d. So what are we talking about? We're talking about a binomial random variable, and we want to say that binomial random variable is very close to its expectation. Well, that's exactly Chernoff's inequality. That's what it is for. Right, so we can just use Chernoff's inequality. Chernoff's inequality. Let me move Chernoff's inequality from that page. So bear with me for a second. I'm just trying to move this statement of Chernoff's inequality, copy, right here. Maybe let's make it blue, like this. So we'll apply Chernoff's inequality for this degree. So it gives us probability that our event does not happen. If it doesn't, the event is good. So if it doesn't happen, then the degree is wild. Then this degree, what is it? 1.1. So it deviates from D by at least 0.1 D. I just rewrote what EI is. So the complement is a bad event, like this. And now we apply this inequality and we get minus, well, delta in this case is 0.1, D over 6, like this. Good. And D, and we know that D is larger than log n, or C log n. So I put it here, so it's larger than 0.1 squared, C log n over 6. Yeah, good. Now the only thing we need is to think now, well, I want this very small. Maybe, I don't know, I want this, whatever, 10n maybe. Can we do this? What allows us to do this? C. So this constant C, we can choose it by ourselves. And we can choose it to be a large constant in this, it's an absolute constant, like 100 or something like this. So I'm sure if you put C to be maybe 1,000, it will work. Yeah, it will work because that will become less than log. And well, anyway, it will work. You agreed? E to the minus log. E to the minus log is 1 over n. And then if you drive C larger, then it should be okay. Okay, so we showed that with high probability, this bad event does not happen. So the good event happens, but for a fixed degree. And now there is a second part of this proof, which is very important, and we will use it many times later. That's called the union bound. Union bound, where we go from a statement about one vertex, one person in this earth, to all of them at once. we would like to have the intersection of all these events true. Right? This is a good event, and we would like all of them to be true at the same time. Yeah. So that's intersect. We'll take intersection of that. So how do we compute that? Well, the intersection is kind of hard to compute. The union is easier. So it's 1 minus probability of the complement, and the complement to the union is complement to intersection is union of complements. Remember this? De Morgan, I think. Do you call it De Morgan's law? I don't know. Take the complement of the union, its intersection, and so on. Okay. So we'll have this. Okay. Now probability of the union. Probability of the union is less than the sum of probabilities. Intuitively should be clear. This is our union. Probability of the union is probability of all these 3 circles is less than if you sum the probabilities of the circles, because some probabilities you'll have some overlap, and that's why you have inequality. And this is, as we know, it's n terms, each of which we prove that this is less than 10 over n, and we get 1/10. So we get that this is greater than 1 minus 1 over 10th, and which is 0.9, and that's it. Good.
I've got a quick question
Yes.
about the proof. In the part where you proved that it is no more than 1 over 10 n big, do you suppose that n big is big enough? Because this will be something 2 multiplied by n big to the power of something.
Yeah, you're right. Do you need that for it? I think so. Yeah, because you need to kill this factor of 2 here. Maybe. Oh, maybe not. I'm not so sure. Do you need it?
You need to get multiplier 1 over 20, actually. So n to the power of something should be small enough to be smaller than 1 over 20.
Yeah, maybe. Okay, maybe. Okay, we can throw that in for free. So I'll also say n is greater than absolute constant C1. Let's say n is also large. We can, if we do that, Vladislav, will this resolve the problem? I think we'll be okay, right? This one.
Yeah, that should work.
That should work, yeah. So these constants, we can choose them ourselves, and this this assumption is not very restrictive because we're trying to model large graphs, so it's okay if we assume that the number of vertices is large enough.
Actually, as long as it is not a 1, we can pick such a big C, but of course for example, for 2, this C will be very large and practically not very good for to use this in practice.
I agree. So maybe n greater than 2, and the statement will work, of course. Now, okay, thank you, Vladislav. Let's make 3 remarks about what Vladislav said, and this is kind of an important thing. 1, is about constants themselves. In this theorem and in many, many theorems that people prove, they prove it for sloppy constants. Where, okay, maybe C is larger than 1,000,000 and things work. But then other people come and always ask, right, well, how realistic is this? And they say, okay, let's work harder and let's kind of tighten this constant together. And other people say, oh yeah, instead of doing this Chernoff, you can do this little trick and this improves in this little case, and this constant need to be optimized even further and further and further. And they do a proof which is maybe 3 times larger, but with very optimal constants that's good in practice. So this is how it works in reality, right? People first write the paper and say, okay, this happens with whatever constants they are, and then later people screw this up and say, okay, tighten, we can tighten everything. So, and that's why in this course, we're okay with just being very sloppy here and putting these large constants, because later we could always come back and tighten them up. Very similar to how you build a mechanism or electrical network, or maybe some computer code. You first make a sloppy work and then you tighten everything up and make it more neat. So we're doing the sloppy work a little bit just to illustrate this concept. Yeah. But it's good that you noted that n is greater than 2 is needed there. Of course, it is. Second comment is about just the architecture of this proof, and I will stop here. This is an archetypical proof by union bound. We need to prove something for all degrees, for all these people on the planet at the same time, that everything for all of them are good simultaneously with large probability. How do we do this? We first prove it for one person. So we fix I. We prove it for one person using concentration. Then we take the union bound. We say the concentration is so good that the probability for one person is extremely large. And then we can take the union bound, which is this, which improves this result for all people simultaneously. And that's how it will work in many results in high dimensional probability and data science generally. Good. Went over time, I'm sorry. Any other questions? Yeah. Okay, perfect. Yeah, we'll see you on Wednesday, and I will stay longer if anybody wants to talk about something, about homework in particular. I know Ladisla wants to do that, and we will stop recording at this time.